I will be discussing about the compaction of soils, or in other words the compaction characteristics of the soils. Well, this is a very significant discussion, and most of the infrastructure which is being developed in present day as well as in the past, it has been mostly by utilizing the properties or the characteristics of the soils when they are compacted. So, it is a very significant discussion in the realm of geotechnical engineering. So, to begin with, the compaction process is basically a densification of soils by imparting mechanical energy. Now, the whole idea of compaction is, when we say densification, what it means is that the gamma dry of the material is increasing and the void ratios are decreasing. All right. So, this is what densification is. It mostly depends upon the gradational characteristics of the soils. Of the type of the soil, and when we say type of the soil, it is a big matrix which has to be defined. Primarily, if I say that this is the fine grained material or the fine grained soils, or the coarse grained soils, so primarily it depends upon the type of soils which you are dealing with. It so happens that the fine grained soils can be compacted in different, by applying different techniques. Mostly we use tamps or hammers. One of the word of caution here would be, when you are dealing with the fine grained soils and when you are tamping them, and if the soils happen to be saturated, the chances are that pore water pressure will develop. So, we have to be careful when we are tamping the whole thing. I hope you understand what are the issues associated with the pore water pressures when they develop in the soils. So, if pore water pressures develop, the effective stresses decrease. Sometimes the fine grained soils are also compacted by falling weights. Check it on net, some good examples of how these compaction techniques are being utilized for creating different strategic and important infrastructure, most of the time the airports and the seaports. We have kneading compactors. Sometimes the compaction can be done by static pressures. The most classic example of fine grained soils being compacted is sheep foot roller. if this is a drum, on this drum you will find protrusions like this. So, this becomes a sheep foot roller. Basically, there is a philosophy behind creating these type of rollers. This also gives you the kneading compaction. You are enhancing the surface area of the compactor by creating these types of protruded elements. So, each time when this system enters the soil mass, this surface is available for compaction process. Not only the small a to a, by providing these type of protrusions, I have enhanced the surface area to A, B, C, A. So, in other words, the surface area gets enhanced and hence the compaction can be done better. You can impart energy up to great extents to the soils. Sometimes the pneumatic tire are also used. So, these are different schemes of compaction and the tools which are used for compacting the fine grained materials. The general word of caution is try to understand their limitations and ill effects before you use them. On the contrary, the coarse grained soils are compacted, not compacted, we can't compact coarse grained material, remember, we densify them by using vibrations. So, most of the devices which are utilized for compacting the granular materials would be a sort of a compact vibrator. These could be handheld plates. Whenever you get time, please go through the net and realize that why structures are failing because of lack of proper compaction. So, these are handheld plates, vibratory rollers. Sometimes we also use falling weights. This is called as dynamic compaction. I have been involved with several projects in the Middle East and in certain parts of Russia, in our own country, in the deserts where it becomes very difficult to compact the soils, and then you have to design a scheme of densification of coarse grained materials, which becomes very interesting. By the way, Indian Army also uses this concept when they do ballistic tests of detonators. So, this is a very interesting subject to pursue research on and to help the country and the society. I can do densification by passing the shear waves, all right. So, imagine that if this is the soil mass and somewhere here if I am having a detonator or a weapon, all right, and then if I charge this, I can densify the sands. So, this becomes densified sands. Most of these schemes are taught when you take a advanced course in ground modification or soil improvement. These techniques are normally applied for ground improvement. So, my suggestion is please go through the videos which are available on modification of the soils by using different techniques. As far as the compaction is concerned, what is the basic objective? So, the basic objective is I want to reduce settlements. Subsequently, we will be talking about how to compute the settlements of the foundation and the infrastructure which is made up of the soil and resting on the soils. So, most of the disasters which I showed you in the problematic soil sometime back in a PPT, the main cause of most of the failures could be the lack of compaction or poor compaction. The another objective is to enhance the shear strength of the soil, and third objective is to reduce the permeability. You may say this is sort of a treatment which you give to the soils which are ailing. So, when somebody approaches you to give a solution to a situation, it so happens that if I want to reduce the settlements, I have to compact the soils. If I want to increase the shear strength or the bearing capacity of the soils, I might have to compact them, or if I want to decrease the permeability, I would like to compact the soil. These are the objectives. Incidentally, the compaction procedure in the laboratory was proposed by Proctor, RA 1933, and hence the test which is normally done to check the compaction characteristics of the soils is known as Proctor compaction test. This becomes a benchmark for testing the soils. All right. I am sure you must have realized that I have used the word compaction characteristics. So, one of the clever ways of using these characteristics would be to classify the soils. So, one of the ways I can classify the soils would be based on the compaction characteristics. So, you may say that Proctor compaction can also be used to characterize So, I am sure you must have realized that there are several schemes of classification of soils which we have developed by this time, starting from genesis to creation to the transporting agencies to the 3 standard techniques of USCS, ISSCS, AASHTO, USPR, and then now I am using the compaction characteristics. Philosophically, when you say that I would like to utilize this property to understand how easily compaction can be done, this is a response of the soil to external loading. To external loading, particularly external loading could be either static or dynamic. In soil mechanics, geotechnical engineering 1 course, mostly I will be dealing with the static case, but when you become a consultant, you will be dealing with a lot of dynamic issues, and one of the dynamic issues I have talked about over here, that military of the country would like to test the weapons, and one of the best ways to test them would be in deserts, or the second one could be you go to the sea and detonate your weapons and see what is the destruction capacity of the weapons. Now, the compaction characteristics would depend upon some parameters. Here I was talking about this. So, densification would depend upon the gamma d, the moisture content, the compaction energy. So, E I am using as compaction energy. And normally we quantify this as compaction energy per unit volume of the soils. Type of soil, and sometimes also under the conditions, whether it is a lab test which you are doing or a field test. So, this is the matrix. These are the uncertainties associated with the compaction process. The compaction would depend upon the gamma dry, moisture content, compaction energy. Type of the soil is a very big term. It would mainly talk about the plasticity index, particle size distribution characteristics, specific gravity also, organic matter, alright, and so on, carbon. So, organic matter, one of the offshoots of the organic matter could be percentage carbon content. When you deal with the industrial issues, there you find that carbon is the most notorious thing. What it does, it absorbs moisture and then it creates a lot of problems as far as the compactability of the soils is concerned, alright. When we say compaction process in the laboratory, there are few parameters on which the entire thing depends. We first say weight of the hammer. This you must be doing in laboratory, I am sure. And this is the modified Proctor. I will talk about this slightly later. So, weight of the hammer, height of the drop, number of drops, number of layers of soil, volume of the mold, so basically you are mimicking what can be done in the lab in the field by creating the situations in laboratory. It so happens unfortunately that whatever can be done in the field cannot be 100% replicated in the laboratory, particularly for the materials which require vibrations. So, it is very difficult to do vibration of coarse grained soils. One of the good applications of compaction of coarse grained soils is what companies like Keller and all are doing. You must have come across the name Keller. These are the champions in designing the stone columns on which nowadays most of the seaports, airports, roads, everything is sitting. So, this becomes a good example of, we also call them as vibros. So, these are sometimes stone columns or vibros. So, coming to this point, Proctor test, normally this is 2.6 kg and modified Proctor test is 4.9 kg. Height of the drop is 31 centimeter and here it is 45 centimeter. Basically, why the name modified has got added up to the Proctor test, because you are modifying the compaction process. So, I will show you how the volumes energy can be computed, and number of drops are normally 25 here, we keep them same, and number of layers are 3, 5. So, if I am compacting a soil mass, suppose if I have to create a filling, alright, this is the existing ground level and I want to create a villa for you, let us say, which is sea facing. So, somewhere here if I want to store water, I have to compact the soil. So, this becomes a retaining structure. Alright. So, this is the compacted soil. This becomes the compacted soil mass, and in the process what I have done is I have elevated the ground level from some value to x plus y. This is the engineering. In standard Proctor, if you compute the total energy, which will be equal to m into g into h multiplied by number of layers. If I define this layer as n and number of layers, say L, alright, number of drops, I will define this as say ND, and this is divided by the volume. Volume normally we keep constant as 1000 cc. So, if you compute the energy, is the height of the weight which is falling of this magnitude, number of layers, number of drops, number of layers, and per unit volume. So, if you compute that, you will be getting some numbers like 593 kilojoules per meter cube, and in case of the modified Proctor, you will be getting 2704 kilojoules per meter cube. Suppose, I mean, one of the very poor type of construction because of which the failures are occurring is contractors do not do compaction in layer. So, ideally if I have to achieve this from x to x plus y, I should be dividing each lift. This is what is known as lift. Each layer is known as lift, alright, and this lift should be 300 mm thick. So, what I will be doing is I will be just laying the soil first, more than 500 or 300, compact it, achieve the dye density and moisture content which I need, and this is how I am attaining up to x plus y. So, this is a cumulative effect. Each layer is being compacted by n number of drops, total number of layers, and we assume that the mass is becoming homogeneous. So, this gets multiplied by ND, and height of the roller or the height of the hammer which is falling is 2.6 multiplied by 31 in the laboratory. Here I can achieve the entire thing by creating a tetrapod. This is how the field dynamic compaction is done. So, suppose if I have to compact the soils over here, I will arrange a tetrapod. This type of treatment I have done in several buildings and several ports in India as well. So, this is a tetrapod. I will create a pulley system, connect a heavy weight to this, and I will drop this weight which will hit over here, and once it hits over here, you get a depression. This is a densified soil, all right, and then you can achieve the state of the material down below of that particular gamma D and moisture content. Is this okay? A lot of added information I have given to you. What is the methodology of doing this compaction in the laboratory? And what is the interpretation of the results? That is very important to understand. You take the dry soil, sometimes oven dried, all right. I hope you understand what type of soils have to be oven dried and what type of soils need not to be oven dried. Weigh it and pass it through 475 micron sieve. Whatever gets passed over, we add water to, suppose if I use the term WP, or let it be W, I think it will give a wrong notion. Let us say this is W prime, all right. To this W prime, we add moisture content in stages. Normally, we add 5%, 10%, 15%, 20%, and so on, depending upon the material. And then you leave the sample for maturing. This is what is known as maturing of the sample, particularly when you are dealing with fine grained materials. So, the procedure is that you take the soil, spread it on a thin polystyrene sheet uniformly, use a hair sprayer and sprinkle water, keep the entire thing in the polythene bag, and by using your hands, but without touching the soil, you rub it. So, the moisture becomes uniform, and then the whole system is normally kept in a humidity chamber. Fine. After 3-4 days, you should be performing the test to get good results. So, I will be now discussing the interpretation of the results, which is going to be useful for understanding the compaction characteristics of soils. This is a typical way of plotting the graphs or the data from the compaction test. On y axis, we plot gamma D, gram per cc. Though I am using the word or the symbol gamma D, I think you should permit me to use gram per cc, though technically it is not correct. So, I can change this to kilonewton per meter cube also, all right. It depends upon what you are using. And x axis is moisture content. You know how to obtain moisture content. So, after 3-4 days of humidity chamber storage of these samples, you take them, keep them in 3-4 pads, weigh them, dry them, again weigh them, find out the difference of the moisture which has been lost, and that gives you the moisture content. So, typically we get some points like this, experimental results, all right. Looking at this graph, I can get the complete understanding of the material. A typical bell shaped curve, all right, indicates a material which is quite easily compactable. You remember when we were talking about the PSD, particle size distribution, we were talking about 3 types of soils, gap graded, well graded, poorly graded, and this is where I had used the word the well graded soils only can be compacted properly. So, this appears to be a well graded material. the particle packing is such that all the bigger particles will allow the finer particles and finest particles to get assimilated in the matrix in such a way that you get a very good density of the mixture. Mostly this type of relationships is exhibited by silty, sandy, clay material. Soils, all right. Clays cannot be compacted so easily. So, if somebody asks you to plot the graph merging on the same graph as of this, the relative position of the clays could be something like this. What this indicates is clays cannot be compacted. Why? Electromagnetic forces. You can't bring the particles closer to each other, and that too by applying mechanical energy, because remember, this is the response of the soil when you are applying mechanical energy to this. So, by virtue of fine grained material being a fine grained material and lot of electromagnetic forces which are active on the surface of the grains of the clays, they cannot be compacted. It is going to be a flat curve. Sands very difficult to compact by this type of compaction unless you go for the vibratory system. So, Proctor compaction curve, this is what is known as a Proctor compaction curve. Rather than saying curve, you can also use the word characteristic. Characteristic is more scientific and technical, and I can interpret it the way I want. So, this is Proctor compaction characteristic. Sands cannot be, so not valid for sands. Fine. So, what should be done? Vibrate them, create a vibratory system and densify the sands. Next time when you go to IIT Jodhpur, it is a beautiful example of how sands have been densified to lay the foundations in the dune, or what we call them as the aeolian type of soils, which I was discussing some time back. So, the point I am trying to highlight is, just by looking at the nature of the graph or the compaction curve, I can infer that what type of soil I am dealing with, and hence this becomes an interesting way to classify the things. Now, what is the interpretation of the curve? If I say this is gamma dry and moisture content, if this is the graph, Proctor compaction, and I am sure you must have realized the moment I enhance the energy of compaction, it becomes modified Proctor. So, if I superimpose for the same material Proctor compaction and modified Proctor compaction, this is how the curve would shift. All right. This point is designated as WOMC. So, for a material, this WOMC is a fingerprint. Now, how you want to utilize fingerprint of a material, it depends upon you as a technologist. Clear? So, this is one of the fingerprints of the material which we have captured. Coming to this one, this is what is known as gamma D max. Clear? So, the moment I have described two parameters, gamma D max and WOMC, I need not to bother about any material, about the material properties anymore, because these two are the characteristics of the material when it is getting exposed to external loads. As an engineer, I am more interested in observing how the soils are going to behave when they are exposed to external loading, static loading. Clear? Is this fine? The logic here is when you have enhanced the energy, the particles become much closer and the water retention decreases. So, this is the WOMC corresponding to modified Proctor, and what happens is gamma D increases. It's okay. Is this part clear? So, if you remember the matrix which I wrote, that why you do want to densify the soils, the first objective was to reduce the settlements. I have made a system more stronger. Imagine when you started from this point where the densities are extremely low, you added a bit of moisture, and what water does in the grains of the soil, it reinforces the particles, provides more strength, gamma D increases. Alright, you keep on adding water. What is enhancing? Gamma T total, and gamma T upon 1 plus W is gamma dry. So, the more and more moisture you add up to a certain extent, the gamma dry will get changed, it will increase, a peak value comes beyond which it drops down. Fine. In modified thing, the water retention drops because the pores have become absolutely small, and this water is going to sit in the pores, if you remember. So, modified Proctor compaction is the characteristic of the soil which gives you the minimum possible moisture holding capacity at optimum. However, this gives the maximum possible density which a system can attain. Now, this is the domain in which you have to work as a technologist, as an engineer. You got it? How best you can compact things at the site would define how best you are utilizing the material. Are these statements okay? Are you able to follow this? So, the trick is how much I can utilize this material to create a system which is very dense. The moment I have achieved this, the shear strength is going to be maximum, the permeabilities are going to be less, settlements are going to be extremely less, and hence I have done engineering with the soil mass. Is this part clear?
According to the formula, that gamma dry is equal to weight of solids upon total volume. So when we add the water, the volume increases, but the weight of soil doesn't increase.
Just
so
give me 5 minutes, I will clear all your doubts. Just hold on for 5 minutes. All right.
Sir,
If you have anything else, then we can discuss.
what are these terms? SS, K, and that?
Shear strength of the soil, hydraulic conductivity of the soil mass, compacted soil mass. Remember, shear strength of the compacted soil mass, hydraulic conductivity of the compacted soil, settlement of the soils which are compacted. Okay. Any other question? Anything else? Did you follow the logic? What water does to the soil? So, when you add little bit of moisture, the water gets remained into the pores, air is expelled out, weight of the water is more than the weight of the air, the unit weight of the soil water matrix increases. Beyond a certain point, this is also what is known as the maximum capacity of the soil to retain moisture, because if you start compacting beyond this point, water being incompressible will come out of the compacted soil mass, and this water cannot be retained over there. So, now answering your question, the way we do it,
Sir,
if yes,
does WMC is actually saturation point?
no, I will introduce the concept of saturation after 10 minutes, alright. Let us go in stages. You understand the basics, then all these terms will come automatically, you need not to bother. So, suppose let us talk about his point first. At this point, normally what we do is, we know the weight of the soil, alright. We know the volume, that means we know the gamma T, remember, no confusion. Is this okay? So, the mold which you have taken, in which you have packed the soils in number of layers by imparting number of drops, clear? You have created a dense matrix, you know the weight of the compacted soil in volume, gamma T is known. Take some of this soil, obtain moisture content by oven drying and compute gamma D. Is this okay? This is the right way of doing things. Is there any confusion now? I am plotting this moisture content with respect to gamma D. Remember, when I was teaching 3-phase diagrams, I had used a word. Gamma D is a normalized form of gamma T. So, gamma T has been normalized with 1 plus moisture content. The tendency of the analysis which normally geotechnical engineers adopt is to filter out the moisture. So, what I have done here? By normalizing the total unit weight with moisture, I am getting rid of the moisture component, and I am talking about the matrix which is in the dry form. Is this okay? Fine. What was your question? I think this is what you have been asking, how to compute gamma D.
But in this case, with the gamma T will always be a constant.
It need not to be constant. So, remember, you started from point 1, all right, point 2. So, what has happened? You have added more water, and that is what I was giving you the logic. In a dry soil, when you add water, the air gets expelled, weight of the water is higher than weight of air. So, what you are doing is you are traversing on a curve where the gamma T is becoming more and more as the moisture content increases.
Gamma T is also increasing and RW is also increasing.
What is RW?
It's moisture content.
Moisture content, yes, that is right. So, from point number A to A, what has happened? The more and more moisture you include in the system and compact it, the total density increases. Clear? And because of that, gamma D increases. Okay. At this point, when the optimal is reached, this is the maximum possible water holding capacity of the soil, beyond which, if you compact, water being incompressible will come out of the soil matrix. It will start draining out. We call it as a bleeding of sample. Is this okay? Further addition of moisture, what is going to happen? It is going to reduce the gamma T itself. Clear? Because now the soil is becoming more and more dispersed. I will use these terms in another 5-10 minutes. Clear? And hence the gamma T is dropping down, but moisture is still increasing. So, it is becoming a sort of a slurry, but not a full slurry. It is a semi-solid material which is being compacted. Is this okay?
So means according to our normal formula, gamma dry is equal to weight of that solid compacted soil upon volume. So as we are increasing the moisture content, our volume is
1 minute. W corresponds to each observation point of the sample. Volume is fixed, gamma T is known. Clear? Corresponding to this state, W is known and hence gamma D is known. So, that means this point is known. I can plot it over here. In the same soil mass, you enhance moisture. So, what is happening? You are traversing on the right hand side of the x axis by adding more moisture. This point comes over here. Weight has also increased. Now, this weight W has become W2. Okay. Volume remains constant, gamma T has increased, W has become W2, and hence gamma D has become gamma D2. So, this process goes on from A to A, very close to the optimal. It's the basically what happens is you are displacing a lighter fluid air by a denser fluid water. So, compaction is the process by which you are expelling out air from the voids of the soils. Is this okay? By filling the voids with water. If I say A to A prime and B prime to B, any compaction curve will have 3 parts. Now, this is what is known as dry of optimum. All right. A prime to B prime will be near optimum, and B prime to B wet of optimum. Is this okay? Fine. Now the interpretation starts, how I want to use it for my engineering design. What you are talking about is, what we do is we benchmark our compaction effort by drawing a line. This is what is known as zero air void line. We normally define this as AV equal to 0. This is the place at which SR is equal to 1, hypothetical situation. You must have noticed we have been talking about the situations for the soils which are non-clay soils. All these results are valid for non-clays. And I said the moment you achieve optimal and the moment you add moisture and compact it, water comes out of the soil. Clear? So SR equal to 1, this is also known as saturation line. So if this line is the saturation line, let us say 1 1, 0 air voids would be AV equal to 0. Is this okay? Did you get the answer to your question? So saturation is somewhere here. If I draw a line which is like this, these are the contours of saturation. Now coming back to your question again, so you know the relationship gamma D is equal to G into gamma W over 1 plus E. It's of not going to be much use to me if I try to interpret the results by using this equation. Why? Because there is a foreigner sitting over here in the form of E. So I have to get rid of this E. How can I get rid of this E? Is this okay? You got it? So what I have done, I am plotting the compaction characteristics on a 2-dimensional plane, gamma D and W, and the contours are of S. So this is your SR. That means the equation for a saturation line would be gamma D equal to G gamma W over 1 plus GW over SR. Is this okay? Fine. So the moment S is equal to 1, this is a normal equation, G gamma W over 1 plus GW. So G is very important to be determined for the soil. Remember, any mistake which you are going to do over here would get reflected in this. Is this part okay? Have you understood this saturation thing? So these are the contours. What it indicates, at this point the saturation of the sample is equal to this, which I can compute from here, because gamma D is known, W is known, clear, G is known, SR can be obtained, clear. So very intelligently we are plotting 3 characteristics on a 2-dimensional plane. Density of the matrix for a given moisture content and what type of saturation you have achieved. I am sure you will realize that AV is nothing. Can you tell me what will be the value of AV in terms of porosity and saturation? So if I say porosity of the system is known, what will be the AV value? How many of you agree with this? 1 minus SR is what? What is SR? Saturation. 1 minus SR is unsaturated state of the material. This is the porosity, volume of voids divided by total volume, clear. So what you get is the AV value, fine. Now what you try to do is, you should prove that gamma D equal to G gamma W 1 minus AV over 1 plus E. Now this is a very interesting equation to analyze. Is this correct, Rajit? Let us check it. So, suppose your soil is fully saturated, AV value is 0, G gamma W over 1 plus E is gamma D. Philosophically, what you are doing is you are applying a correction factor of 1 minus AV to the density of the dried material. This is the way to remember this. 1 minus AV is a sort of a saturation value for the state of saturation which is not 100%. How would you use this? I mean, this is just like a cardiogram of a patient for a surgeon. If I get a relationship like this, and if I know this is 100% saturation, the deviation from the saturation line is an indicative of the compaction efforts. Most of the projects in the country are ailing because of this. Go to the site, collect the sample of the failed embankment, bring it to the lab, reconstitute it, recompact it, and prove how much gamma D OMC you are able to get. Get this test done 5 times, you have the statistical value. Take the samples from the field. You remember core cutting method, density displacement method and all, balloon method, nuclear density gauges which I have talked about. Check the value which you are getting in the laboratory from density gauges by core cutter method, balloon method, and that is it. See, the point is you cannot compact a material with the same energy. So, this curve is energy specific, clear. So, here what has happened, in this direction the energy increases, clear, fine, but saturation line remains constant. Why? Because this is material specific. Remember, depending upon the material which you are compacting, this G remains constant, and hence the saturation line is material dependent, it will not shift. If I am compacting a material somewhere here, that means gamma D and W corresponds to this. I have already shown on paper that what was desired was this, and where the material was compacted is like this. So, if you are sitting somewhere here, this much should have been extra required in the compaction process, which has not been achieved. Now, one of the ways of interpreting these results would also be, what you have realized is that a compaction curve has a peculiar bell shaped characteristic. Nobody asked this question, that for a given gamma D, there are 2 values of the moisture. You know, this nobody asked. So, we have point 1, we have point number 2, and there must be a reason for this. The reason is, if you look into the microstructure which we have talked about, the grain structure of the soils, this side is flocculated system. However, as you keep on imparting more and more energy in the form by adding more moisture, what happens is this flocculated system gets converted to dispersed state. You remember, we have talked about the grain structure of the soil. From a disorderly state of the grains have become ordered by adding more moisture. So, what moisture does to the soil? It acts as a lubricant, fine. So, the more and more moisture you add, the particles, the grains start slipping over each other, they become more ordered, you are compacting them. So, they have got aligned like a ferromagnetic material, where the ferromagnetism takes care of the alignment of the magnetic poles which get created in the system. So, truly speaking, 1 and 2 are very interesting parameters or state of the material for the same gamma D for a person who is into construction industry. All right. One of the interpretations would be, if I plot gamma d sorry, if I plot hydraulic conductivity as a function of moisture content, it's a beautiful example of how two types of mechanisms can be superimposed on the compaction characteristics. You remember when we were talking about the flocculated soil structure, I had used the word that this is going to be more porous as compared to the one which is more dispersed. So, that means the hydraulic conductivity is going to be dropping very significantly, and this is how the curve looks like. So, in the flocculated state of the material, you have high permeabilities. At OMC, this is the minimum, K minimum, and beyond OMC, it picks up a bit. Why? Because look at the graph, your gamma T is decreasing in this region, is it not? In this region, the gamma T picks up. So, this is where the system is becoming denser, and this is where the system is becoming less denser. So, less density because of dispersed state is going to create lower permeability. This type of arrangement of the grains is going to restrict the movement of any type of fluid through this. So, if I was a petroleum geophysicist and if I do an exploration in the middle of the sea, and if I get the samples of the soils which are totally dispersed, and this is how most of the wells are discarded, because a dispersed structure, because of its structure is not going to allow the permeation of the fluid so easily. It is going to be very zigzag. There is a lot of hindrance which the particles are going to create for the movement of the fluid as compared to this system where the fluid movement could be easier. So, this is one of the ways to match hydraulic conductivity, moisture content variation with gamma d moisture content variation on the compaction curve. This point still remains partially unanswered, that what is the difference between 1 and 2 when the gamma d is same. Now, this is what is known as the dry state of the material in terms of gamma d, and this is what is known as the wet state of the material. The compressibilities of the system are going to be totally different when you compare 1 and 2. So, what is the difference between 1 and 2? The compressibility is going to be different. So, if you are making a cricket pitch, or if you are making an embankment, or you are making a airstrip, or if you are making a earthen dam, or you are making a foundation system, you have to be very careful about where you are going to compact and what point you are going to select for constructing the structure, whether the wet of optimum or dry of optimum. Now, the logic says wherever the water logging is going to take place, like earthen dams, where you do not want water to percolate through the compacted soil mass easily, because that is the whole idea. I should be compacting the material at gamma d wet. Why? Because the hydraulic conductivity is less. You got the answer? However, when you are creating an embankment for the traffic or runway, where you want cross drainage to occur, it will be a good idea to talk about the gamma d which is on the dry side, because this system shows more strength as compared to this system. The flocculated structure is much more capable of taking higher loads as compared to the dispersed load. In dispersed load, if you remember, the settlements are going to be a big issue. So, this type of information can be deciphered from a simple test which is known as compaction test. Clear? And that is why I was saying let us use the word compaction characteristics and not only the compaction curve. Characteristics are much more broader, and they connote a lot of information about the material as compared to the curves. Now, we have been talking a lot about the fine grained materials. What about the coarse grained materials? There is a phenomena which is associated with the sands. If you try to compact them, this is what is known as bulking of sands. geomechanics is very closely related to the thermodynamics of the material. You might get a chance to study the thermodynamics associated with the state of compaction of the material, because I am sure you must be realizing when you are compacting the soils, what you are doing, you are imparting energy to it. So, if you use the concept of energy conservation, which you might have done, you can make an interesting model where certain amount of energy which was in the form of potential energy gets converted into kinetic energy. A hammer falling from a certain height comes and hits the soil mass, potential to kinetic, and look at this is the sample of the soil. Now, when densification is taking place, your gamma d is increasing, that means the grains are coming close to each other and system is becoming more dense. So, there is a relative movement of the particles because of the impact. So, this kinetic energy gets converted into the energy of the particulate system, clear, and air is entrapped inside, which has a tendency to come out. So, this becomes a kinetic process. So, it will be a very interesting idea to do a energy modeling of the compaction process, fine. So, what happens here is when you talk about the bulking of sands, you know, it is a very funny material. What is observed is that initially the gamma d decreases when you add the moisture into sands or sandy soils, attains a minimum value of gamma d and then it rises. This behavior is known as bulking. We will be analyzing this behavior based on the shear strength theory in the second course, which is going to be more rigorous than the first course. This is a introduction to the subject. What is the interpretation? When you add moisture to sands, fine sands, the density drop is because of the surface tension, clear. So, this is the process in which the surface tension is resisting, you know, the compression of the particles. You keep on adding more and more moisture, surface tension gets dissoluted. That is the wrong word, dissoluted, but what I am trying to indicate is it disappears. So, by adding more and more water, this is approximately at 2 to 3% by weight. So, bulking moisture content is 2 to 3% by weight, beyond which the capillarity is lost. The more and more water you add, the air gets expelled, the density increases. Now, this whole process is known as bulking of sand, and this is where you get 20 to 30% of gamma d. So, if I say this is gamma d initial, this would be gamma d final, which will be an enhancement of 20 to 30%. Is this okay? If I further play with this graph, in the previous lecture we have been talking about effective stresses and the suction and the pore pressures. So, I would like to complete that series. So, if I define UW with respect to moisture content and this is the OMC, what will happen? The more and more you compact the soil, you are expelling the moisture, clear. So, the pore water pressures are going to be not pore water pressure, let us use the word suction, negative pressures, pore pressures. So, what what's happening is the more and more you compact, the more and more air gets expelled out, the suction increases. At OMC, this is the maximum possible moisture which the system is having, but just to left hand side of this, the system has maximum possible suction in it. These type of situations are going to be extremely problematic. You imagine every year in Bombay city, the tracks get flooded during rains, alright. So, imagine that you have created an embankment, rains come, water logging takes place, and close to OMC, you have maximum suction which is getting developed in the system. Given a chance, because of this suction, the tendency of the material would be to suck most of the moisture which is available freely, and hence the soil mass beneath the track becomes wet. Are you realizing this? So, next time when the trains move, what is going to happen? These equal amount of the pore pressure is going to get developed, and hence your effective stresses are going to decrease. So, it becomes very tricky to operate trains or the infrastructure, vehicular traffic, if you are not taking care of how to compact the soils. Clear? So, the best way would be go to the wet off optimum, there is no suction getting developed, the volumetric deformations are going to be extremely less when you are dealing with the wet state of the material. So, core of the dams are mostly compacted at the wet of the moisture content for the same gamma d. This is okay. Two advantages I am getting. First thing is the permeabilities are going to be low as compared to the dry state of the same gamma d, and second is the settlements and the lateral deformations are going, not lateral, vertical deformations are going to be extremely less when I compact the material at the wet of the OMC. Clear?
How can our gamma d can be negative?
Gamma d is not negative. The suction which is getting generated in the soil, this one here, it is not negative, it is decreasing. There is a decrease, there is a drop in the initial gamma d, it is not 0 0. Whatever density you started with, dry density, because of addition of water, there will be a drop of 2 to 3% because of surface tension, and when you keep on adding more and more moisture, the surface tension is lost and the density starts increasing. Fine. So, I was talking about the compressibility here. Normally, compressibility is a function of range of stress. Sometimes we define things as a low stress, and sometimes we define this as a high stress. So, suppose if I plot void ratio as a function of stress, I will use the term as stress for the time being. When we are dealing with the low stresses in ranges of kilopascals, fine. This is the response of the soil on the dry of optimum and wet of optimum. What I am trying to show here is wet of optimum for low stresses in the kilopascal range, the volumetric deformations are going to be more as compared to dry of optimum. Clear? Fine. This graph continues as if I have broken the axis. and if I am dealing with the very high stresses, it has to be plotted on a log scale. We normally do not take the log of the number, we plot it on a log scale. That means this has shifted from kilopascal to megapascals. So then you are plotting it on a log scale, clear? What is the interpretation? This remains the dry of optimum and this becomes the wet of optimum. On the wet of optimum, the volumetric reductions are going to be less for higher stresses as compared to dry of optimum. I repeat, when I was talking about creating the core of the dams sites are approximately few hundreds of meters or maybe few tens of meters depending upon the type of dam you are constructing. So, the chances are that you are going to work in the log of stress ranges. When you are compacting the soil at wet of optimum, the volumetric deformations are going to be less, clear, as compared to dry of optimum. So, this point becomes an obvious choice. When you are dealing with the low stresses, railway tracks, transportation systems like pavements, low stresses, the philosophy is different. The dry of optimum deformations are going to be lesser than wet of optimum. You can select depending upon this. Is let us say, we were doing in the previous lecture the state of stress and I had given you some idea about the compacted state of the material. If you remember, since my 4th, 5th lecture I am talking about variably saturated soil mass. Okay. So, say water table is here and I had put a condition that if I compact this soil mass or layer heavily and if this happens to be fine grained material, let us say, what is going to happen? So, first thing is because of the capillarity associated with the compacted material which is of fine grained type, if I consider a point over here at a depth of let us say Z and the thickness of this layer is Z1, and if I consider a point over here let us say point P and this is Z2, and if I ask you to compute at point P what is state of stress, sigma P, pore water pressure at P and the effective stress at P. So, this becomes an interesting case. It is not difficult, I hope you can solve it still. You remember the concepts of finding out the pore water pressure here? If this is the capillary zone, you will have to put a tensiometer here, you can compute the UW value. At this point you are trying to find out, this is the capillary zone, this is the peak of the capillary zone. You should remember this is the capillarity. So, this is the maximum value of this is the maximum value of the capillarity, remember, clear. So, this is going to be gamma W and what is the funda? You have to put the tensiometer over here and then find out what is the drop in the water head. So, this is Z1 minus Z and negative value. Is this okay? Finished? At this point, it's simple. You put a piezometer. So, this becomes your Z2. So, at this point, I know the value of UW, I know the value of sigma. Sigma is going to be tricky. Why? This is the saturated system, this is saturated, this is dry, depending upon the material property. It's okay. So, you have to be careful. This problem is a real life problem, which if you solve would teach you a very interesting lesson, that why we should not use fine grained materials in retaining wall. Or for backfilling for that matter. Because you should prove this whole layer acts as a surcharge. What is surcharge? In your engineering mechanics course, you must have done these problems. There is a container which is filled up with some fluid, say water, and then you are pressurizing this by injecting a gas into it. All right. And if I say that the gas pressure is P, and if I ask you to find out the pressure at this point at a depth of Z over here, so this is the P pressure which is acting constant, and this will get added up to, so this is P, which I can show like this also, uniformly distributed load. You must be doing a structure analysis, plus this is the hydrostatic pressure. Is this okay? So, when you have the fine grained material which is heavily compacted, this becomes a sort of a surcharge which is equivalent to P. Because of these surcharges, the earth pressures which are coming acting on the retaining system will go up, and that becomes a big issue. So, I have talked about compaction process today, compaction characteristics, how to interpret the compaction curves, how to use these compaction characteristics in designing different structures, and the most critical one is the beautiful example of compacted fine grained material, how it acts